Welcome back. In today's lesson, we are going to talk about perpendicular bisectors and angle bisectors. And so we're going to start out just taking a look at what it means to be a bisector and what it means to be perpendicular. In the diagram on the left here, we have a line CD, and this line is perpendicular to segment AB, and that's indicated by the right angles. So anything that's perpendicular to another line forms right angles. And in addition to that, we can tell that it bisects segment AB because of the markings given on here. And it says that AD is congruent to BD. And then over on the right-hand side, we also have two other segments drawn in. And those segments give us two triangles. So what we've done is we've just connected A to C and B to C to give us two triangles. Now, the work we've done in Chapter 4 on proving triangles congruent, we know already that we have an angle congruent and a side congruent. So we only need one more piece of information to prove that triangle ADC is congruent to triangle BDC. And we notice that segment CD is common. So these two triangles are actually congruent by side angle side. So that's a little review of what we did in the last chapter. So since we know that these two triangles are congruent, we also know that side AC would be congruent to side BC, and that is because they are corresponding parts of congruent triangles. Once we've proved these triangles congruent, all their parts are congruent, and one of those corresponding parts are the hypotenuses of the triangles. So one of the things that we can say, there's a new term for you here, is that any point on this line, we're going to get a theorem here real quick, any point that's on this perpendicular bisector is said to be equidistant. Equidistant just means equal distance. So any point that's on this perpendicular bisector is an equal distance away from the endpoints, A or B. Here are our two theorems then, and the theorem says if you have a line that's perpendicular to a segment and it's a perpendicular bisector, so it bisects the segment and it's perpendicular to the segment, then any point on that line, if you were to connect any point on that line to the endpoints, it will be an equal distance away. So PA and PB will be equal in measure. The converse of that theorem says that if you have two segments, PA and PB, that are congruent on a triangle, then the line PM that you create that's perpendicular to AB will be a perpendicular bisector, where AM will be congruent to BM and PM will be perpendicular to that segment. So let's go ahead and start solving some problems using these theorems. This problem says, what is the length of side AB? Well, we are given in the figure that the length of side AB is equal to 4x, and we are given the length of side BC is 6x minus 10. And we have some indicators in the drawing that segment BD looks like it is a perpendicular bisector. It is perpendicular to AC, and it's bisecting AC. So we could say that BD is a perpendicular bisector. So B is equidistant from A and from C. And what that means is we can set BA equal to BC then, because it is on the perpendicular bisector line. So BA is congruent to BC, but then we can substitute what those equations are, 4x for BA and 6x minus 10 for BC. And then we can solve that, subtracting 6x from both sides. We get minus 2x equals minus 10. And lastly, dividing by negative 2, we get x equal to 5. But that's just finding what x is equal to. We want to know what the length of side AB is equal to. So now we need to take that x and plug it back in to the 4x, which was the equation for what side BA was equal to. So we're going to go ahead and substitute that back in. AB was equal to 4x. So 4 times 5 gives us 20. So side AB is equal to 20 units. Here's one for you to try on your own. Go ahead and pause the video and I'll give you the answer when you come back. All right, hope you gave that a try. Looking at the markings on the drawing, QS is a perpendicular bisector, so it is equal distance from P and R. So then we can say 3n minus 1 is equal to 5n minus 7. And I'm going to go ahead and just subtract 3n from both sides. So minus 3n and minus 3n. And then when I subtract those, I should get these two canceling. And I have a negative 1 still sitting there is equal to 2n minus 7. And I'll add 7 to both sides for my second step. Plus 7 and minus 7 add to 0. So I still have 2n is equal to a minus 1 and a plus 7 is a plus 6. And lastly, divide by 2. And I get n is equal to 3. So does that answer the question they asked us to find? Well, what is the length of QR? Well, QR right here is 5n minus 7, so I need to substitute that in. So 5 times whatever n is minus 7, that's what QR is equal to. But we said that n was equal to 3, so I want to go ahead and substitute that in. So that gives me 15 minus 7, which is equal to 8. Right, here's another problem. It says a park director wants to build a t-shirt stand equidistant from the roller coaster and the spaceship chute. So here's the roller coaster, here's the spaceship chute. That's hard to say. What are the possible locations of the stand? Well, if we want it to be equal distance from these two, and we could go ahead and connect those two with a line and then find the midpoint of that. Okay, so if we went ahead and did that, we might have a drawing something like this. R for roller coaster, S for spaceship chute, and go ahead and connect those, find the midpoint A, and then construct a perpendicular bisector. So anything that would be on this line would be equal distance from roller coaster and spaceship chute. Okay, so as long as we had something that was on that line, we would satisfy those requirements. Well, what if that director wants that t-shirt stand to be equidistant from the paddle boats and the spaceship chute? Well, the paddle boats are up here. That's letter P, so we have that over here. So if we want it to be equal distance from the paddle boats to the spaceship chute, well, then what we have to do is we have to go ahead and connect point P to point S, okay? And we would have to find the midpoint of that segment, okay? And so I'm just going to go ahead and assume that the midpoint's about right here, and we would want to construct this to be a right angle. So this is not necessarily a right angle here, but I'm just going to say that it is. We're going to say that it's pretty close. So I'm going to give us the right angle thing in here. So let's suppose that's a right angle and that's the midpoint. So anything that would be on that vertical line would be equal distance from the paddle boats and spaceship chute. Now part B of that says, can you place the t-shirt stand so it's equidistant from the paddle boat, spaceship chute, and roller coaster? Can we have it equidistant from all three? And the answer is yes, we could do that. It would require that they would be at the intersection of those two lines. So the original line L and the line that we constructed, that intersection point right there is where the t-shirt stand would have to be. It would be equal distance from paddle boats and spaceship chute, and also from the roller coaster because it's also on this line. So the distance from a point to a line is the length, it's along the perpendicular segment. Okay, from the point to line, that's actually the shortest distance from any point to a line. The shortest distance is what you would get if you were to construct the perpendicular to the line, and that would give you the shortest distance there. So in this diagram, we have ray AD is a bisector of angle CAB, so it's cutting this angle A here in two equal parts. And if we were to measure the perpendicular distance anywhere on ray AD, we would find that those distances would be equidistance. Okay? So that gives us two more theorems, the angle bisector theorem and its converse. The angle bisector theorem says if you have an angle bisector, ray QS, and it bisects an angle and it's perpendicular to 2 points, to point P and to point R, then what happens is the length of SP and the length of SR are equal. Okay, they're equal distance from those points where it's perpendicular on the sides of the angle. The converse of the theorem says that if you have two segments that are perpendicular to the sides of an angle and they are equidistant, then the ray that you would create by connecting Q to that point would be an angle bisector. It would bisect the angle. So how can we use that to solve some problems? Well, in this problem we have a figure over here on the right, and we want to find the length of segment RM, and that's given as 7x. We also know that segment RP is 2x plus 25, so we're going to go ahead and use that angle bisector theorem. We see that NR is an angle bisector, and these are perpendicular, so we know that they are congruent, so we can go ahead and substitute those expressions. 7x equals 2x plus 25. Subtract 2x and we get 5x is 25, or x is equal to 5. But we needed to find the length of RM, so we have to substitute x back in. We've solved for x, and now we need to put it back into our expression, and we get RM is equal to 35. Here's one for you to try. Go ahead and pause the video, and we'll work through it together when you get back. All right, I hope you gave that a try. Let's see what we come up with. It looks like ray CF is indeed an angle bisector. These are perpendicular, so we can say the expressions are equal. So we're going to say 6x plus 3 is equal to 4x plus 9. All right, so let's go ahead and subtract 4x from both sides. Go ahead and solve this equation. When we do that, okay, the 4x's cancel here, and I have 2x plus 3 is equal to 9. My next step is to go ahead and subtract 3 from both sides. Getting pretty colorful here. These add to 0, so I have 2x is equal to 6, and my last step is to divide both sides by 2, divide by 2, and 2 divided by 2 is 1, so we just have x equals 3. Well, once we have that, we need to plug it back into the expression for segment FB. And segment FB was 6 times x plus 3. But we found x was equal to 3. So 6 times 3 is 18, plus 3 gives us 21. So that is the length of segment FB. Here's your lesson check. Go ahead and work these out and have those ready to turn in to class when you get into class next time. See ya!